Greetings and welcome, friends. We're taking a look at page 518, problem 25, 15 plus 10, 25. We're talking about solving polynomials using quadratic techniques. Wonderful stuff. This problem here, well, if you cube root both sides, you'd end up with one of your answers, but I have a hunch. I'm interested to see what happens if I subtract 1331 from both sides, and I'd get like a b cubed minus 1331 equals 0. And I'm tempted to see if this might be factorable. Is 1331 a perfect cube? Let's see, what is the old cube root of 1331? Is that 7? Oh, it's 11. I lied. A lot of times palindromes like that. A lot of times, what am I saying? That powers of 11 are palindromatic. All right, so that's a difference of cubes, if I might say so myself. So if you just cube rooted both sides on this problem, you would have gotten just the 11 answer, but you actually would have been missing two other roots that you were unaware of. Now, the fact that this is a difference of cubes, whoop, there we are. I can use the difference of cubes pattern. A cubed minus b cubed is equal to a minus b in parentheses times a squared plus ab plus b squared. There we are. And so I'm going to just factor this super quick. I'm going to have b minus 11.
I have a question.
Yeah.
Can you teach us this, or is this like...
Yeah, this is a pattern we learned back in the day.
Yeah, but like, how are you supposed to know to apply it?
Well, whenever you see a difference of cubes, you'd have to realize, this one and this one? Here? No. Let's see, plus 11b plus 11 squared is 121 equals 0. So now I've got two things that multiply to be 0, so I could set each of them equal to 0, so b minus 11 equals 0. You can see that when I solve that, I would just add 11 to both sides, and I would end up with the answer that you would have gotten if you just cubed rooted both sides. So I'd get b equals 11. So there's one of my solutions. But this other one is of far more interest to me. B squared plus 11b, that's not a 116, plus 121 equals 0. I believe typically these will not be factorable right there. So I'm going to actually, let's use a quadratic formula, the old quad form. A equals 1, B equals 11, C equals 121. Make sure you're writing this down if you got this wrong. Here's some gold coming to you. So let's plug this in the quadratic formula and solve. X equals the opposite of b plus or minus the square root of b squared, it's 11 squared, 121, minus 4 times a is 1 times c is 121. Let's see, I got all those signs right? I think so. All over 2a. Right? Yeah. Yep. I've got my pattern right. Yep. Okay, yeah, these are actually going to be imaginary roots, but we can still solve them. Negative 11 plus or minus the square root of 11 squared is 121. Minus 4 times 121, it's going to be what? 484, is it? Negative. And it's negative. All over 2. So I'm going to get x equals negative 11 plus or minus 121 minus that, what's that? 363. Negative 363. Good save. Thank you, friend.
What's the next test going to be worth?
Don't worry about it. We're doing the homework right now. Let's just learn everything we can and get those points we can get. 363, that feels square rootable, but it's not. Does 9 go into that? Yeah, 363 divided by 9. No. 363. Is there a perfect square that goes into 363, guys? No. Oddly enough, 11 does twice. Yeah, 121 goes into it. Ah, silly me. So I could actually break this up into negative 11 plus or minus the square root of negative 1 times 121 times 3 all over 2. And my answer reveals itself. X equals negative 11 plus or minus. Square root of 121 is 11. Square root of negative 1 is I times the square root of 3 all over 2. And I can't simplify that any further. So I have 3 solutions. 2 of them are imaginary. 1 of them is real. And not just real, it's also rational. So good problem right there. Thanks for asking it.
I thought it was impossible.
No, that was 21. Let's take a look at 27 here. It says z minus 8 roots of z minus 240 equals 0. So the idea is I want to figure out, can I pretend that this is a quadratic? So could I pretend this was something like this? 240 equals 0. And if I did, what would go in those parentheses? Square root of z, and it matches in both cases. Which it has to, right? So 8 times the square root of z is 8 square roots of z, and root z squared is z. All right. Technically, you might even be able to argue that's the absolute value of z, but we won't worry about that right now. So I'm going to make up my own variable. I'm going to say variable w is equal to the square root of z, and I'm going to replace that and solve it quadratically. So w squared minus 8w minus 240 equals 0. So now I can factor this. This is a quadratic. I know how to solve that. I didn't know how to solve this thing up here. Actually, well, you might have. If you solved using radical equation techniques, you could have. However, we're going to continue solving using quadratic techniques, which won't be that bad. So I'm looking for the factors of 240 that have a difference of 8. I'm guessing they're going to be further down on the list. Let's keep going. 3 goes into that's 40, 80 out. 4 goes into that 20, 60. Yep. They're getting warmer. 5 goes into 60. What's that? 10, 12 times 4, 48. So 5 and 48. 6 goes into 60 10 times, 6 and 40. 7, I'm thinking 7's a no-go. 8, I think 8 works. Yeah, 8 goes into 45 times 5 times 6 is 30. Oh, I'm getting warmer. 9, no, I think there's only one multiple of 3 there. Yeah, for sure. 10, yeah, 10 goes into 30 3 times. 3 times 8 is 24. Ooh, 14 apart and getting warmer. 11 doesn't work. 12 goes into 24 twice. 12 and 20. Ding, ding, ring-a-ding-ding-ding. Right there. So I found the multiples of 240 that subtract to be 8. So I'm going to have a w with a 12 and a w with a 20 equals 0. Their signs have to be different since they multiply to be negative. They add to be negative, so the more influential one must have been the negative one. So that would be a negative and that would be a positive. Set both of these guys equal to 0 and solve w plus 12 equals 0. W minus 20 equals 0. Solve it, friends. Minus 12 plus 2o plus 2o. Bado, here we go. W equals negative 12 and w equals 20. Now, if I say the answers were negative 12 and 20, I'd be wrong.
You have to square or root them, right?
Well, they were interested in what z is equal to, not w. I made up w, so I'm going to have to say, well, square root of z is the same as w, so let's plug this back in down here and rewrite this in terms of z. Right? So substitute back in. So the square root of z equals negative 12. The square root of z equals 20. And when I square both sides, you see that z is equal to positive 144 or z is equal to 400. Now, if I do a check back in the original problem, we might see a mistake here. Let's do a quick check. Check it. Check. Let's check 144. So that would be 144, what was it? Minus 8 times the square root of 144. What was that? Minus 240 equals 0, I believe is right. So 144 minus 8 times, what's the square root of 144? That's 12, friends. 144 minus 80 plus 16, that's what, 96? Did I make a mistake? Oh, okay. But you're saying to 144. Yeah, clearly, yeah, 144 minus two things, one of these things being bigger than, it's not going to end up equaling 0. But 144 minus 96 is 48 minus 240 is what, negative 200. No, wait a minute. Negative 192. Not equal to 0. So that means this is not true because that is an extraneous solution. Let's do the same quick check this time for 400. 400 minus 8 times the square root of 400 minus 240 equals 0, question mark? We'll find out. Minus 8 times, not 12, 20. Oh, classic. That looks like that's going to be 160 in the negative range, not 1600. It ain't don't live on Pennsylvania Avenue. Let's see, this is 240 minus 240. Oh yeah, 0 equals 0. We're good. So that means a legitimate solution is 400 to the original problem, and it turns out I only have one solution there. Not too shabby. Let's see, take a look at one more problem real quick. How are we doing for time? 12 minutes already. I might just show the setup on this problem. So I want to pretend, can this be rewritten as a quadratic? Plus 20 equals 0. So what would go in those parentheses? Y to the 1/3 power. Yeah, this is a 1 right here. And then that's a 2/3 power, but y to the 1/3 squared is 2/3, so that works out. So it does appear this works. So I'd make up my variable. I'd say, I don't know, u is equal to, or u r y equals 1/3. U is equal. U r? Yeah, sure. So I would be able to write this as u squared minus 9u plus 20 equals 0. Oh, this factor's fast. Let's just finish it. Why not? Our YouTube friends can all just stop watching if they wanted to. 4 and 5. Let's see. Add to be 9, right? That looks like 4 and 5 to me, friends. So I'm going to get u with a 4, u with a 5 equals 0. Double negative because they had to multiply to be positive, so the signs are the same. Add to be negative, that's the only way that works. U minus 4 equals 0, u minus 5 equals 0. Cruising. U equals 4, and u equals 5. U are 5. So I'm not interested in u, I'm interested in y. Sorry to break it to you. It's over. So here we are, we've got y to the 1/3 equals 4, y to the 1/3 equals 5. How do I get rid of a 1/3 power?
IDK, how to do this.
Yeah, it turns out you could cube both sides. If you don't like that step, I could rewrite y to the 1/3 power as the cubed root of y. And then maybe that would be more clear to you that you would cube in order to undo that. But look at this, 1/3 raised to the 3rd power, you'd multiply those, that'd be 3/3 power, reduces to 1. Y to the 1th is what I'm looking for there, right? So over here I'd get y equals 4 to the 3rd, what's that, 64 I think? And over here I'd get y equals 125, I believe, if I'm not mistaken. So I'm not actually too worried about checking this because these are cubed roots. They don't, I don't believe they have extraneous solutions like square roots would have. And also these were both equal to positive numbers here anyway. And just checking the answer in El Libro, yeah, both of those are legit anyway. But yeah, so that's the idea to these problems. Pretend that they're quadratic, solve them using quadratic techniques, resubstitute back in, and then solve for your original variable. It's rather a clever trick. This is also referred to as U substitution because the variable U is most frequently used. U substitution is a skill that is even used in calculus when finding, I believe, derivatives and integrals and such. So it ain't going away in a long time. So thanks for watching, Internet friends. Bye-bye.